Hello everyone. In this video, I am going to talk about section 5.1, conditions for rigid body equilibrium, and also section 5.2, free body diagrams. We're going to look at quite some free body diagrams today. So in contrast to the forces on a particle, the forces on a rigid body are not usually concurrent and may cause rotation to the body. So in order for a rigid body to be in equilibrium, the net forces needs to be equal to zero. Sum of all the forces needs to be equal to zero. And also the sum of all the moment needs to be equal to zero. Okay. So sigma F equal to zero, meaning there's no translational motion. Sigma moment equal to zero, meaning there's no rotational motion. We need both of them in order to say this rigid body is in equilibrium. For an analyzing purpose for an actual physical system, we usually create an idealized model, and then we draw a free body diagram showing all the external forces, and we also write equations to solve for the unknowns. This one, for example, we have a beam. There's an external force being applied to the beam. We're going to idealize the model. We're going to draw like a free body diagram to outline the shape. We know that there's external force 1200 Newton being applied 2 meters away from the fixed support at point A. We know there's the weight of this beam. And we know that for fixed support, your reaction force is going to be AX and Y and the moment at point A. So we're going to draw the outline shape, and we'll also show all the external forces, including the couple. Apply load, support reaction, and the weight of the body. Um, the support reaction for fixed support, I will show you more diagrams in a little bit. But for fixed support, you will have reaction force on the horizontal direction AX, reaction force on the vertical direction AY, and also the moment MA to prevent it from rotating as well. So we're going to label loads and dimensions on the free body diagram. All known forces and couple moments should be labeled with their magnitude and direction. For unknown forces and couple moment, use the letter AX, AY, moment A. If it's like point B, you will be BX, BY, and MB to indicate any necessary dimensions. A few examples over here. Roller support. Think about the office chair that we're sitting on. It's got roller at the bottom. There's no horizontal constraint. When I say horizontal, it's like parallel to the surface constraint. There's no constraint parallel to the surface. There's only support perpendicular to the surface. So this one, because it's not flat on the ground, this roller support is not flat on the ground. That means the support will be perpendicular to the surface only. For pin support, you have reaction force Fx and Fy, horizontal reaction and the vertical reaction as well. And then for the fixed support, you will have not only horizontal Fx, vertical Fy, you will also have the moment to prevent it from rotating as well. So the pin support you can rotate, right? But the fixed support you cannot rotate. So here's the example. So this echo what we talked about in the first example back before in that beam. As a general rule, if a support prevents translation of a body in a given direction, then the force is developed on the body in the opposite direction. And if a rotation is prevented, then you will need a couple moment in the opposite direction. So this one right here, if I have my foot on the pedal, foot coming down vertically, that means I will have reaction from the link B, and then I have reaction force from the spring, 30 pound, both of them are horizontal to the right. And notice that at point A is going to be a pin support. That means I have my reaction force AX and AY at point A. Next one, idealize the model. We're going to make it 2D. Point A is going to be a fixed support. Reaction force from point A, where you will have AX and AY. And then you have this cable supporting at point B. That means you have a tension, same direction as the cable, you have a tension. And then also you have a weight of the entire platform overall from the center of gravity of the platform. This one, we're pulling down with 300 Newton, 30 degrees away from the vertical direction. That means you have your support reaction from A, from B, and from C. And notice that reaction force will always be perpendicular to the surface of contact. So that's why your NA is at a 30-degree angle, because we have 30-degree here. That means reaction perpendicular to that will be 30-degree as well. Normal force in B will be straight coming down, because we have a horizontal pipe. And then on this direction, on this section of the pipe is horizontal. And then also normal force C vertically going up as well. This one right here, your support reaction at A is going to be perpendicular RA. Okay, there's no other constraint. It's free to slide up and down at an angle on this pipe. So only RA perpendicular to the surface. External force 100 pounds. And over here, B is a simple support, right? It's not a pin support. It's not a fixed support. Simple support at B. That means you only have the reaction force RB perpendicular to the surface. And then that 200-pound foot is external moment provided. Okay, so this is all I want to show you for 5.1 and 5.2. Thank you for watching.